Look at this water. This is a raw, turbulent river current, the primary source for thermal power plants. To safely spin a steam turbine at 3,000 RPM, this fluid must be transformed into highly pressurized, ultra-pure steam. In its natural state, this water is a chaotic suspension. It contains floating organic debris, dissolved gases like methane, and microscopic colloidal particles that refuse to settle out. Pumping this raw fluid directly into a high-temperature boiler creates a catastrophic risk to the plant's metallurgy and human safety. The engineering challenge is one of scale. A standard thermal plant intake, such as the Bandewadi facility, must process 200 million liters per day of this heavily contaminated municipal or river water. At this scale, raw water is incompatible with power generation. It requires a multi-stage intervention before it can ever reach a boiler tube. That intervention happens in the pre-treatment plant, or PTP, a series of precise chemical reactors engineered to eliminate specific impurities before they destroy downstream hardware. This table maps microscopic water impurities to the failures they cause. Total hardness, specifically dissolved calcium and magnesium, leads to the formation of insulating scale on the interior walls of boiler tubes, which blocks heat transfer. Chlorides are equally dangerous. If left unchecked, they aggressively attack stainless steel components, resulting in stress corrosion cracking, or SCC. Then there is silica, or silicon dioxide. This impurity bypasses basic physical screens and carries over into the steam, forming an impenetrable glass-like scale on high-speed turbine blades. The PTP must strip these impurities from the water, reducing their concentrations from high parts per million down to trace parts per billion. By absorbing this bulk impurity load, the PTP protects the sensitive downstream demineralization plant from rapid degradation. The process begins here at the first node of the pipeline, the cascade aerator and pre-chlorination stage. Inside the cascade aerator, raw water falls over staggered tiers, releasing corrosive volatile gases like carbon dioxide and methane into the atmosphere. The aerator also maximizes dissolved oxygen levels to trigger the oxidation of inorganic impurities. These equations detail how dissolved oxygen reacts with metals. Soluble ferrous and manganese bicarbonates convert into insoluble iron and manganese hydroxides. In parallel, chlorine gas is dosed to physically destroy the cellular material of microorganisms through pre-chlorination. This process achieves maximum oxidative efficiency when the water is maintained within a precise pH window of 6.5 to 7.0. Phase 1 neutralizes biological threats and forces invisible, dissolved metals into a physical form that can be targeted in the next stage. The next challenge involves suspended colloidal organics. These particles are too microscopic for physical screens. A chemical paradox keeps them suspended. These particles carry negative charges, causing them to repel each other in constant Brownian motion. To break this, aluminum sulfate is dosed into a flash mixer. Positively charged aluminum cations attach to the colloids, neutralizing charges and eliminating repulsive forces. For alum to successfully precipitate as aluminum hydroxide, the raw water pH must be maintained between 5.0 and 8.0. The neutralized water then enters the flocculation zone, where low RPM paddles gently agitate the fluid. This gentle mixing, often aided by polyelectrolytes, encourages the neutralized particles to collide and stick together into large, heavy masses called flocks. Coagulation and flocculation use chemistry to force unfilterable threats to become macroscopic, physical targets. Entering the clarification zone, the process shifts to bulk physical separation. The clarifier drops the water's upward velocity to near zero. Without upward momentum, gravity pulls heavy flocks downward, forming a thick sludge blanket at the bottom. Clarified water rises and spills over the weir. Operators must periodically pump out this accumulating sludge to prevent the system from failing. This stage achieves the bulk removal of the suspended silts, organics, and precipitated metals engineered in the previous steps. Even after clarification, microscopic, buoyant microflocks can manage to escape over the weir. These are captured by routing the water through rapid gravity sand filters, or advanced fiber disc filters. Operators must initiate a backwash sequence whenever the differential pressure, or delta P, exceeds 0.3 kilograms per square centimeter, or every 24 hours. Before the water leaves the pre-treatment plant, it undergoes a necessary chemical correction, dechlorination. The chlorine dosed earlier is highly oxidative. If it reaches the demineralization plant, it will irreversibly shred the fragile ion exchange resins. To solve this, the effluent is dosed with sodium bisulfite or passed through activated cardin to strip the residual chlorine from the water. This final step ensures the water is physically clean and chemically safe for the downstream resins. This is the completed 6-stage sequence of the pre-treatment plant. Oxidation was required to precipitate the dissolved metals. Coagulation was required to eliminate the electrostatic repulsion of the colloids. Gravity and differential pressure filtering removed the resulting physical mass. Before the water is released, the shift engineer must verify these strict numerical targets. Turbidity must be below 10 nephelometric turbidity units, NTU, and total suspended solids must be below 10 milligrams per liter. Iron and manganese levels must be verified below the 0.1 milligram per liter threshold. Finally, the pH must be stabilized between 6.5 and 7.5, with all residual chlorine removed. Once targets are met, the water is released into the demineralization plant. The pre-treatment plant is a mastered thermodynamic gauntlet, stripping natural chaos from the water to secure the high-efficiency survival of the power station.